Alright, today I thought I'd get into a little bit more technical details on this topic of grid-tied rooftop small wind turbine performance. I've been working, as some of you might know, with Larry Leamy, who's an electrician out in Pennsylvania. He has been experimenting with putting different wind turbines on his house and configuring them with a variety of ways using these grid tie inverters, the wind rated grid tie inverters, and it's an ongoing project. We don't have necessarily a locked-in approach, but we're trying to find out which configurations of turbines, grid ties, and so forth work well together. So where he's at right now is he's got 3 WinMax 5-blade turbines on his house. They're all the same size. They're 59-inch rotor size, but they're rated at slightly different watt level, mainly to indicate which wind level they can most efficiently operate at. The HY400 starts up in the lightest breeze. It has the least resistance on its PMA, and it generates good power at the lighter winds. The 600 in more of a medium wind case, and the 1000 really shines its own when the winds get stronger. So by having all 3 of these, he's able to, in real time, with each one connected up to one or more grid tie inverter, and again, these are the wind rated Sun G grid tie inverters, he's able to accumulate quite an impressive amount of power having this configuration. So I want to share some of the data that he's collected for me and asked me to help plot out and continue on with the implementation. So what he's done is he has up on one of his towers, he has a anemometer. It updates every once per second, and he has it correctly located about 1 rotor length below the hub on one of his towers. Gives him a good exposure to the air, not any obstructions, and then any of the air hitting the turbine itself isn't going to be in the way of affecting what's on the anemometer readout. He also has a watt meter that's connected up to his line going to his fuse box, which collects all of the grid tied power that he collects between the 3 inverters. And I'll show you what a little video of that sample run. So here we are. He has his NV ENVI watt meter displaying his real-time watts that's coming off of his grid tie inverter set, and then over here running on his computer is his in-speed vortex anemometer that updates once per second. So see, so it's every 6 seconds this updates with another reading, so 219, and you can see what the wind speed is here. This just updated here, wind speed here. So my job was to take this data off of these videos that he's been sending me, and this one here is about a 10-minute long one, and plot that data, enter it into a spreadsheet, and try to derive some information from it. So if I go over to my spreadsheet, and I'll show you how I've entered that in here. So we got what I call my slot time, which is basically each time the NV watt meter changes, that's a new slot. It's once every 6 seconds. What the reading was on the NV and what the mile per hour reading was on the in-speed. From that, I'm able to calculate a slot watt second. It's basically how many watts were collected over that 6-second period. And what I do is I just take these beginning number, the ending number, come up with an average number between those two, and apply that for 6 seconds of time to give me a number of watt seconds. I can accumulate that watt seconds as we go down, and then I can also calculate a running average of watt seconds as we run down through the data here. When I get down to the bottom, I'm able to calculate what an average wind speed was for this run, which was again about a 10-minute period of time, what the average watts were. So this would be equivalent to what you would see like on a solar panel if you had kept the solar panel up for this 10-minute period. The equivalent of all this bursty data coming off these wind turbines is averaging about 184 watts continuous. Now I can take this data and plot it out on a curve here. So if you see it down in the green here, I've got my watts plotted on the left axis, and then every one of these green dots is actually a data point from that 10-minute run. And then the green solid line is that running average that I was collecting in the spreadsheet and plotting that out. So that's how I'm able to determine that on average during this period of time, which turned out it was a kind of a windy, gusty day, I was able to get the equivalent of about 184 watts continuous power out of these 3 wind turbines delivered to the grid. I was also, with that same data, be able to generate a pretty good idea of what the wind was doing. This is a little bit of a smooth curve because the actual individual data points was also very spiky, but this gives us a general idea of what the wind was doing. Miles per hour over here, so gusting a little bit over 15, and but averaging with my spreadsheet, I'm able to figure out what the average wind speed was over this period of time, which turned out to be 10.94 miles per hour, which graphically looks about right, just eyeballing it here. So what can we do with this data? Well, the first thing I did is I just took every data point, sorted it by wind speed, and plotted it. And you can see it's quite a scattered set of data. There's some data points that seem to be very high, 600 watts, even over 900 watts. And what this indicates is there are times where a big gust of wind hits, the anemometer is only updating every second, but if you think about an anemometer, you can blow on an anemometer for 1 second and it will spin for probably a good 10 seconds and give you a reading every second for the next 10 seconds. Well, which one of those represents the actual wind speed? That's hard to say. So you're going to get quite a scattering of data, mainly because the anemometer is not necessarily tracking exactly what the wind is doing, because it's trying to calculate that out too. There's no perfect way to measure wind speed. It takes time to measure it properly. But given this scattered data, you can put a trend line in there that gives you kind of a general idea of the power that was being collected by the system relative to the wind speed. So you can see here 10 miles an hour, maybe 130 watts, 15 miles an hour, maybe 240 watts, and that gives you kind of a general idea. Now the next thing I did is I took the data and I said, well, now that I know how many watts and I know the wind speed, how does this compare to the power in the wind to come up with a coefficient of performance? And the coefficient of performance is what percent of the wind power you're actually able to extract. Well, when I compare these blue dots to the actual power in the wind, it ends up telling me that I'm extracting more power out of the wind than's actually there. So that suggests that these data points are either wrong or they're improperly measured, because there's no way you can extract more power from the wind than's actually there. Matter of fact, the theoretical limit is 59%. So technically all these red dots above this 59% point are all incorrect, or any of the blue dots that drove those numbers there. So then I thought, okay, instead of taking each dot, let me just calculate based on this trend line what the coefficient of performance is. Now I can derive what this line actually is. It's a little bit of an exponential value, and I have it up here calculated out. So I can put the number miles per hour times 4.4 to this exponent tells me the watts, and based on that I can plot out what the coefficient of performance actually was using the trend line as opposed to each individual data point. But still, we have quite a few of this above 59%. So that's still telling me that even this trend line, which is driven heavily by a lot of these data points below, is still overestimating what the actual performance is for the system. So the next thing I did is I went in and I edited out data that seemed to be off, out of sync with the actual wind speed. You can see down at this low end here, I eliminated all the scattered points and tried to stay close in. When I started to get quite a few data points up here, I thought, well, I can't just throw all those away, so I kept those in there. And hopefully this second trend line would be a little bit more accurate, but I literally had to throw away about half of the data points to come up with this new plot. Then when I went in and calculated the coefficient of performance with much better set of data, it still gave me some numbers that were quite high as far as coefficient of performance. I really wouldn't expect any to be up near 50 here. So there's still question of, down at this low wind point, really are we able to get up to this 50% level? And what I think is happening here is the anemometer, again, we're talking about 5, 6, 7 mile an hour kind of measurements, and we're probably even with this in-speed instrument, which is actually one of the more accurate instruments, you're still going to get quite a variation of a 1 or 2 or 3 mile per hour difference in the measurement, which has quite a big impact on the calculation. But then again, I can take and put a trend line against that red data, and it's starting to give me a little bit more reasonable output as far as the coefficient of performance for the configuration, trying to get rid of some of the extraneous measurement points. We've also got a little bit better accuracy on our power curve. So when I put it all together at the end, at least this run that we did the other day, this is kind of our smooth current representation of his system, showing the watts versus what wind speed and what the coefficient of performance currently is at. So this is where we're at. We'll hopefully be able to make some improvements from here. If any of you have any ideas of how to do this better or have any comments on it, we'd appreciate it. And thank you, Larry, for all your contributions. There was one more thing I thought of that I should add on to here before I close it out. I went back to this chart here, which actually utilizes the exact raw data that we had from that run, where we had the actual 184 watts going to the grid, which was a legitimate number because it took measurements from all of these data points, these power measurements. We also calculated the average wind at 10.94. So these are some pretty reasonably stable numbers. Now if I took those two numbers together and I know what his total sweep area is, I can calculate what the coefficient of performance is, being able to generate 184 watts at a wind speed of 10.94 miles per hour. And to my surprise, it came out 48%. So either that's extremely impressive or there's something missing from the puzzle. Anyhow, I thought I'd share that. Catch you later.